We're going to talk about direction fields. If I had a first order differential equation here, dy dt equals some function of t and y, geometrically what is dy dt? So thinking of the graph, what about the derivative? So essentially the derivative at a point is the slope of the tangent line to the curve at that point. And so even though I may not know the solution to this differential equation, I know the slope of the tangent to the solution curve at any given point. Because you give me the point t and y, I could put it in the function I had here and I could tell you the slope of the tangent to the curve at that point. Now if I build a graph showing all those little different slopes, it's called a slope field. It's also called a direction field. Those two terms are used interchangeably. You can build or draw a direction field by hand. You can also use a computer to do that. So let's see what it looks like. Here is a simple differential equation, dy dt equal y, and here is the slope field or direction field. And so it's plotting little slopes of tangents to various curves, and you can see that if we put in, for example, 1 here, when y is 1, the slope is also 1. So if we go up here to where y is 1, you can see that we have all these little slopes along here that are at 1. And then if we put in a 2, we would get the derivative is 2. So the slope of the tangent line when y is 2 is 2. So you can see we have all these little arrows of slope 2. And you can see as the y gets bigger, then the slope gets bigger, and you can see these arrows doing this. If y equaled 0, right along here, we would have all these little 0 slopes. Those maybe didn't show up so well, but they're there. If y was -1, you can see along here we have all these little -1 slopes. So you can actually see the solution curve by following the little slopes of tangents to the curve. So I can see that there'd be a curve that would come up something like this. I could see there could be one that would come something like this. There's also one that would come along here like this and stay at 0, an equilibrium solution. So there's varying ones. I can make several of these, but you could get the idea. So what a direction field does is it shows the direction the solution is heading. And if you looked at this one, there's an equilibrium solution at 0, but it's really hard to hit on 0 right exactly. And if I missed it by a little bit, let's say I was sitting here and had the y value being 0.00001, you can see that eventually it's still going to head out and away. Or if I missed it and it was a really negative 0.00001, I'm going to head away. This would be called an unstable equilibrium solution then, because if you didn't hit right on exactly 0 to all digit 0, you're going to either head up or down depending on if you're off a little above or a little below. How would the direction field be different if we had a negative y? Well, you can see if we put in 1, the slopes should all be -1. So at 1, these would all go the other direction. So this essentially would reverse all of the slopes because we're changing the signs on those. So here it is reversed. Now you can see that if I started somewhere here and I traced out the curve, that I would end up approaching 0. I could trace a solution curve this way and I would approach 0, and here is our equilibrium solution at 0. Now if I missed by just a little bit and I was a little bit above, it's going to stabilize at 0. If I was a little bit below, it's going to stabilize at 0. So this one is a stable equilibrium solution. If you're using this to model and build something and you want it to stabilize, you can see this would be the situation we would want. The other one, if you didn't get something exactly perfect, it's going to blow up essentially, and this one is going to stabilize heading towards our equilibrium solution. We could trace out the solution curve that had an initial condition. Then we could give us an initial value, y of 0 equals 1. So this would be the curve that passes through that point and follows that slope field. Let's look at this slope field and see what we can see in it. We have the differential equation dy dt equals y minus 2. Can you see the equilibrium solution here? We can see it just staring at us right here. Here we have zero slope, which means it's not changing. The rate of change dy dt equals 0 anywhere along here. And then we can see what the other solution curves would do if we were a little above or if we were a little below. So we can see that this would be an unstable equilibrium solution at y equal 2. And we could find that if we were looking here, because we could say here is the slope. The slope is y minus 2, or the rate of change. When is the rate of change 0? When y equals 2, the rate of change is 0. So it is in equilibrium, not changing.